Carbon dioxide is a greenhouse gas that has the ability to induce the increase of global temperatures, which can lead to harmful environmental impacts. The main source of carbon dioxide is the burning of fossil fuels, and although in recent years many countries have decreased their carbon dioxide emissions, others have increased, and 80% of global energy needs are still met by fossil fuels. Current global carbon dioxide concentration is estimated to be around 400 parts per million and increasing at a rate of 2 parts per million a year. And studies have suggested that in order to prevent dangerous temperature rise, the concentration must peak around 450 parts per million. In addition to reducing emissions, one approach to abating carbon dioxide concentrations is carbon dioxide capture and storage. Hi, my name is Megan Bushlow, and I'm a rising junior studying civil and environmental engineering at the University of Michigan. This summer, I worked through the SURE program on a research project with Professor Brian Ellis to study one potential method of carbon dioxide storage that involves a process known as mineral carbonation. In practice, the method would involve injecting captured carbon dioxide into rock formations so that the mineral carbonation reaction can take place. In situ mineral carbonation of carbon dioxide has the potential to be very useful for storage because of the large abundance of rock formations that could support this method, and because the carbon dioxide is stored with long-term stability. However, available technology is not sufficient for the method to be applied to large-scale systems because the reaction needs further investigation and improvement before reasonable reaction rates and extents of reaction can be achieved. The overall mineral carbonation reaction consists of carbon dioxide reacting with a mineral to form quartz and a carbonate precipitate. One mineral that has been found to have reasonable reaction rates and is relatively abundant is olivine, magnesium silicate, and the carbonate formed is magnesite. The reaction has two main parts, the dissolution of olivine and precipitation of magnesite. First, carbon dioxide is dissolved in water, which forms carbonic acid and hydrogen and bicarbonate ions. The bicarbonate further dissociates into carbonate and more hydrogen ions. The hydrogen ions are responsible for the dissolution of olivine and results in the leaching of magnesium cations into the fluid and the formation of quartz on the rock surface. The free magnesium ions then react with available carbonate ions to precipitate magnesite. For large-scale application, captured gas would be mixed with a solution of water and some other chemicals and injected into fractured rock formations. The fluid would be preheated to an elevated temperature to improve reaction times. Models and experimental findings have suggested that high crystallization pressures from the mineral carbonation reaction induce further cracking in rock formations. If this could be achieved in application, the newly exposed rock would serve as additional reaction surfaces on which precipitation could occur. Understanding the changes that take place in rock formations during mineral carbonation, including the dissolution of surfaces and the self-driven cracking, is the primary goal of the research with which I was involved this summer. We can study these processes by using a flow-through reactor to push water with dissolved carbon dioxide through a crack in a rock core and then analyzing changes in morphology and composition of the rock. Both before and after setting up an experiment with the flow-through reactor, we get a CT X-ray scan of the inside of the core and compare the images to detect volume changes. After the experiment, we can study the morphology of the rock using secondary electron images and the composition using backscatter electron images. Additionally, we can learn about the dissolution that took place by finding outlet solution chemistry using mass spectroscopy. Another important aspect of my research is the chemistry of the solution with which the carbon dioxide is mixed prior to its reaction with rock. A low pH environment is needed for magnesium dissolution, but a slightly higher pH is needed for magnesite precipitation. Past studies on solution chemistry have found that adding certain alkaline salts such as sodium bicarbonate aids precipitation by increasing pH. One of my goals is to find an optimal chemistry at a set temperature and pressure for our future use with flow-through reactor experiments. In order to begin investigating this, we reacted a small sample of olivine powder with milky water in a batch reactor for 4 days. We studied the olivine particles' morphology and composition using the scanning electron microscope both before and after the reaction, and analyzed the solution products with mass spectroscopy to determine how much, if any, dissolution and precipitation occurred in the system. Next, I will conduct similar experiments with different solution chemistries to determine which one will be most effective for our flow-through experiments.